Okay, so I'm creating this video because I want to summarize the periodic trends so you can understand this better. Remember that I told you the other day that there are three important trends that we're going to analyze in this course because they are important for bonding. And the three important trends that we're going to analyze: atomic radius, electronegativity, and ionization energy. The first trend that I'm addressing in this presentation or in this video is the atomic radius, which is the distance from the center of the nucleus all the way through the borders of the electron cloud. Okay, the distance from the nucleus all the way through the outside or the edge of the electron cloud. Now, what's gonna happen when you go down a group? The atomic radius is going to increase, and when you go across the period, the atomic radius is gonna decrease. But why? What do you think that the atomic radius is gonna increase when you are going down a group? And I have over here the first example. See, I was using lithium, sodium, and potassium just to explain why when you go down a group, the atomic radius is increasing. And the answer is super simple, because remember that I was explaining to you that the period number is given by the principal quantum number, which is the level of energy. So for example, if you have lithium, in this case over here, with an atomic number equal to 3, this is the electron configuration, meaning that you have 2 levels of energy in an atom of lithium. But when you move down to sodium, see, atomic number equal 11, this is the electron configuration for sodium. And as you can see, you are adding an extra level of energy. The same thing happens with potassium, and in this case, remember that the s orbital is gonna be filled, is gonna be completely, is gonna be accommodating electrons before the d orbital, because this one has less energy than the 3d. Okay, but as you can see here in this pattern, as you are moving down a group, you are increasing one level of energy, which is the expected trend, because remember that this number that you have over here, the principal quantum number, is gonna give you the period number in the periodic table. So if you use this point over here as the reference for the nucleus, when you look all the way through the last level of energy, as you are going down a group, what's gonna happen with that distance is going to increase. And I know what is the question that you have right now, okay, in your mind. Oh, Ms. Ramos, are you telling me that as the atomic number is increasing, so is the atomic radius? Careful with that, because if you look over here, across a period, the atomic radius is gonna decrease, and across the period, is the atomic number increasing? Yes, it's increasing as well. However, the atomic radius is gonna decrease. Why? I'm gonna explain you that right now. Okay, why then in a period the atomic radius is gonna decrease? And I was using 3 elements that are located in the same period 2, and I have over here the electron configuration. Why am I showing you the electron configuration? Because I want you to look at the ending. Even though the atomic number is increasing, lithium, boron, and oxygen, they has all the electrons organized in the second level of energy. Ramos still, okay, even though they have the electrons accommodated on the second level of energy, oxygen has more than lithium. You have to look inside the nucleus. Remember that we're looking at the distance from the nucleus all the way through the edges of the electron cloud. What's gonna happen when you go across a period? And look over here, I'm representing over here the nucleus of the 3 elements. as you are increasing the atomic number, see, as you can see over here, only, see, when you go in order, the electrons, they're gonna be increasing by one, they're gonna be accommodated in the same level of energy, but inside the nucleus you have one more proton, but you have also one more neutron, making, the nucleus to grow, if you want to call that, twice faster than the level of energy. The level of energy, they are the same across a period. Level of energy are the same because remember that the principal quantum number is giving you the period number, but the nucleus is growing like super fast. Because when you are increasing across the period, you're increasing the atomic number, you have one more proton and one more neutron. And you know how gravity works, okay? The object with the biggest mass is gonna be attracting the one with the lowest mass. And you know that the mass of the electrons, they are super small. It's so small that sometimes we don't take that into consideration when we are calculating the atomic mass for the element. Okay, so when you have a nucleus that is that big and still the electrons, they can be accommodated in the same level of energy, the tendency is just to attract them, reducing that distance. Remember that inside the nucleus you have the protons that are positively charged, and then you have the electrons that are negatively charged. When you have that amount of mass together with the positively charged particle inside the nucleus, the tendency is just to attract them with more gravity force, and consequently the atomic radius is gonna become smaller as you move across the period. What is the consequence of this? Okay, now the consequence of this is that oxygen, since oxygen has an atomic radius smaller than lithium, oxygen has more control over the valence electrons. Okay, it's gonna be easy to remove the valence electron for oxygen. It's not gonna be easy. First, because when you have that small like atomic radius, the nucleus has a lot of control over the valence electron, and a lot of energy is required to remove them from there. Okay, the same is gonna happen in lithium. No way, Jose. The nucleus of lithium doesn't have like too much control over that electron, that valence electron. What's gonna happen, Ms. Ramos? You already know that if you were in my physical science class. You know that lithium is a metal, and the tendency of the metal is to lose electron. That's gonna happen. Okay, and oxygen is a non-metal. What is the tendency of the metal is just to gain electrons. Okay, that's gonna happen. That's why this lesson is so important, because if you don't understand periodic trends, you're not gonna be able to understand bonding. Now, see, we were talking about metals, gaining and losing. Then we're gonna move to, we were talking about atomic radius, which is the distance from the nucleus of the way through the end of the electron cloud. Now we're gonna move to a trend that is not important, but that we have to analyze, because is what's gonna happen, when the elements they are bonding to reach chemical stability. Okay, two things that you have to be that you need to know before understanding all of this. The tendency of the metal is just to lose electron, and later I'm going to explain why. While the tendency of the nonmetal is just to gain electron. In order for the metals to reach chemical stability, they will be losing electrons. And for the nonmetals just to reach chemical stability, they are gonna gain electrons. Okay, why the nonmetals they are gonna get electrons? While the metals they're gonna lose electrons, because they are following the Diopter rule. no following. It's a tendency that they have. The atoms, they tend to lose or gain electrons to complete a full set of 8. See, according to the Opte rule, in order for the element to be chemically stable, that element needs 8 electrons in the last level of energy, with only 2 exceptions: hydrogen and helium, because they are atoms that are so small that since they are able to accommodate all the electrons in the first level of energy, they don't have to complete the 8 electrons, because remember, the first level of energy is able to accommodate only until up to 2 electrons, and there's no space for more in there. So helium is happy with the 2 electrons on the last level of energy, and hydrogen is incomplete with the one that it has on the first level of energy. So in order for hydrogen just to reach stability, he has to complete that one that he has there with another one on the seat. For the rest of all the elements, they follow the Opte rule. In order to become stable, the tendency is just to reach or to get a electron in the last level of energy. Now, since the metals, they are going to be losing electron to reach that stability, they are forming cations. What is a cation? An ion. And we're talking about, in this trend, about ionic radius, okay? Either the metals, see, they are going to be accepting electrons. If they are becoming negative ions, and the name of for negative ions is an ion. Okay, I put the run over here, an ion. No an onion, an ions. Okay? Now, what's going to happen to the atomic radius down a group? You know that when you go down, you are increasing one level of energy, one level of energy, one level of energy. It doesn't matter if you are analyzing metals or no metals, as you're going down a group, the tendency is just to increase the atomic radius, the ionic radius, because you have extra level of energy. Just because the extra level of energy that you have in there. Now, what's going to happen across the period? That's when you have to analyze the metals and the non-metals. Okay, I have over here example of 3 metals that they are located in period 3. Okay, I'm moving across that period 3. I'm doing the same with the non-metal, but I'm going to start first with the metals. I have over here the electron configuration, because remember, I don't know how many times I have to say you, all the information is on the electron configuration. Okay, so I have over here the electron configuration, and as you can see, sodium in the last level of energy has only 1 electron. Is sodium in compliance with the Opte rule? No. Okay, so it's gonna be easy for him to lose 1 or just to gain 7. And that's what happened over here. When you move from left all the way through the right, but still you are within the metal, remember that the tendency of the metal is just to lose electrons. Why? Because it's easier for them. Remember that they're going to be following the atoms, they're going to be following the Opte rule. And when you analyze over here, you have only 1 valence electrons. And if they need 8 on the last level of energy, is going to be, for example, for sodium, it's going to be easy to lose 1 than to accept 7. For magnesium, it's going to be easy for him just to lose 2 than to accept 6. And the same is going to happen with aluminum. That is going to be easy for him to let go 3 than to accept 5. Now, we are in the same period. When you look at the electron configuration, look at the ending. These 3 metals, okay, and these 3 non-metals that I have over here, when you look at the electron configuration, they are in the same period. So, atomic radius, remember, metals, they are going to form positive ions, cation, by losing electron. So when you are moving from left all the way to right, but you're still within the metals, the tendency of the ionic radius is to decrease, because they're going to be losing more electrons as you move from left all the way to the right. But then, when you get same period, When you get into the same period to the non-metals, look at this. This is the ending. This is phosphorus. Valence electrons, 5. Remember the octal rule, okay? It's gonna be easy for him to let go 5 or to accept 3 of them for a total of 8. So it's a different story. You remember that the tendency of the metal is just to accept electron. Eh? So phosphorus is gonna be accepting 3. Sulfur is gonna be accepting 2, and then chlorine is gonna be accepting 1. Since when you move within the same period but on the non-metal side of the periodic table, when you move from left to right within the non-metal part of the periodic table, they are going to be accepting less electrons. Consequently, see, the tendency is to decrease that ionic radius because they are forming negative ions, and as you're moving within the non-metal in this direction, left to right, they're gonna be accepting less electron until you get to the noble gases that they're not accepting any electron at all because they already have an electron on the last level of energy. So what is the tendency of the atomic radius? One more time, and let me summarize this. In general, when you go down into a group, the atomic radius is going to increase because of the extra energy level. In the period, what's going to happen? When you move from left to right within the metals, the tendency is to decrease because they are losing more electrons as you're moving across the period until you reach the non-metal. Within the non-metal, they are going to increase when you start with the first non-metal because they are gaining, and then the tendency within the non-metal is just to decrease one more time because they are gaining now instead of losing. Within the metals they were losing. As you were moving from left to right, they were losing more until you reach the metal that they're going to start gaining. But as you move within the non-metal, they're going to be start gaining less. So the tendency is to, like the general tendency in a period is just to decrease and then increase in the non-metal and decrease one more time until they reach the halogens. Okay, quickly, over here, ionization energy, and you have the definition over here. Ionization energy is defined as the energy that is needed to remove one electron. Okay, so you were learning before that the metals, they're going to lose electrons, and the non-metals, they're going to gain electrons. When you look at any given period in the periodic table, they're going to move from metals all the way through non-metals. So if you look at period 3, you're going to start with metals, transition metals, and then all the way through the right, you have non-metals. If metals, they are losing electrons, it's going to be difficult to remove the electrons that they have in the last level of energy. No. So when you move across the period, the ionization energy is going to increase. And that makes sense because the non-metals, they are accepting. They are not giving away the electrons. So it's very difficult. Let's say that you want to remove the 7 electrons from the electron cloud around a chlorine atom, and you need a lot of energy. Why do you need a lot of energy? Because remember, the atomic radius is small because all the electrons, they are attracted to the nucleus, and the nucleus has control over the electrons, so it's going to be very difficult to remove them. What happened with the non-metals? See, that the nucleus is going to be easy for the nucleus to let go the 1, the 2, or 3 electrons that they have in the last level of energy. Okay, so they don't have control over that. And as you move down the group, since you are adding more level of energy, so the nucleus is not going to have full control of the electrons on the last level of energy, so it's going to be easy to remove them from the electron cloud. Easy and simple. One more time. Ionization energy is decreasing in a group because of the extra level of energies that are there, in a period is gonna increase because you are moving from metal to non-metal, and the metals they are losing electron while the non-metals they are gaining that. And because also this is another trend, because when you move in a period, what's gonna happen to the atomic radius is gonna decrease. So it's gonna decrease due to the fact that the nucleus has more control over the valence electrons of the non-metals than in the metals. Okay? Super important trend, electronegativity. Electronegativity is the ability to attract the electron. One more time, guys. We have been discussing this for the past half an hour. Who are the elements that are accepting electrons? The non-metals. So when you move from metals left all the way to right, non-metals, the electronegativity in a period, the electronegativity is going to increase. The tendency of the metal is just to lose electron, while the tendency of the non-metal is just to accept that. Why? Because of the Opte rule and because the ionization energy. Remember that metals, they have valence electrons equal to 1, 2, and 3, and it's easy for them to let them go than that to accept 5, 6, or 7. Okay? Remember that nature is always going to do work using the less energy. Is that what happened here? The metals, they're going to let go the electrons that they have in the last level energy, in the last level of energy, and the non-metals, they are going to be accepting them. Consequently, in a period, see, the ability to attract the electron is going to increase. Now, what's going to happen in a group is going to decrease. Why? Because if you keep adding more level of energy, it's going to be very difficult for the atom just to attract electrons, keep the electron cloud together, and attract more electrons. Okay, you have this information over here in case that you want to read that. You have that information there in the picture that I was attaching to this slide. Okay, you have that here in case that you want to read that. Ms. Ramos, why is this so important? I'm going to explain you right now. Let's say that you have two electron configuration. This is an element X, and I have over here element Y. You don't have a periodic table. I'm not giving you a periodic table. The only thing that I'm giving you is the electron configuration. What are the things that you can do with electron configuration? Look over here. That's the electron configuration. When you look at the ending, this element is going to be located in period 3, group 1. How many valence electrons? Only 1. How can you classify that element? As a representative element, and in this case, since it's located in group 1, is an alkali metal. You know that the alkali metals, they are soft, so soft that they can be cut with a plastic knife. They are highly reactive. They react strongly with the oxygen, with water, with halogens. They have a silver color, physical and chemical properties. Knowing the electron configuration, you can get all that information, okay? And in addition, okay, you have another element over here. When you look here at the ending, SP, you have another representative element that is located in the same period, period 3, but in group 17, okay? So another representative element that since it's located in group 17 can be classified as a halogen. Okay, group 17, halogen, 18, noble gases. You already know that. Okay, since you know that it's a halogen, they are non-metals that reacts aggressively with alkali and alkaline earth and other metals. Okay? Now, let's say that I want to know between X and Y which one has a higher electronegativity. Easy piece, okay. See? same period, but this is in the Y one is located in group one, the X one is located in group one, the Y one is located in group 17. You are moving across the same period, so the halogen has a higher electronegativity. Which one between X and Y has the biggest atomic radius? And in that case, it's gonna be the metal, because remember, when you are moving across the period, when you go from left to right, the atomic radius is gonna decrease. So this one is gonna have more atomic radius than this one over here, okay? Because they have electrons organized in the same level of energy. Still, what happened with this? Has more protons and neutrons inside the nucleus, and consequently it's gonna be attracting all the level of energies towards the nucleus. Okay, so see all the information that you can get from the electron configuration without looking at the periodic table. Now, this is for the next unit. Why is this so important? Ramos, what do I need to know? That the Y is more electronegativity, or has more electronegativity than the X. Why is important to know that the ionization energy, which is the energy to remove electron. See, this one over here, the X, is gonna have less ionization energy than the Y. Why is that important? Because okay, when elements, they are looking for stability, they are gonna start bonding together. And look over here. See, ionization energy less than in this one, so it's gonna be easy for this element just to lose that electron. Who's gonna gain that electron? See, the Y element is gonna gain that electron, and that's how X and Y, they're gonna be able to form an ionic compound. X is gonna lose the electron, while Y is gaining that electron to form a compound. And that's why all of this is important, because all these periodic trends, they're gonna be explaining the bonding between elements. The X has less ionization energy than the Y. Consequently, Y, since has more electronegativity, is gonna be able to steal that electron that is needed in the p orbital from the Y element, from the X element. Okay? And that's how compounds are formed.